Hi there, and this is a lesson video, exercise 7b on now differentiating inverse hyperbolic functions. You may recall that the last video looked at differentiating inverse trigonometric functions, and to be honest there's a big overlap between the two methods. So bearing that in mind, let's get going. I want to do the first two starter questions using first principles, so effectively looking at cosh and sine in terms of their formulae in e to the x. So bearing that in mind, if I differentiate cosh, this is like half e to the x, so I still get a half e to the x when I differentiate it, because you remember that differentiating e to the x gives you e to the x. But when I differentiate the half e to the minus x, I get minus e to the minus x over 2. And that, of course, is equal to sine. And that's the rule that we should know, that cosh becomes sine. You should also remember, of course, that sine becomes cosh. So let's just prove that as well. Starting here now, if I've got that and I differentiate it, this is a half of e to the x, so that's just a half of e to the x. But the minus and minus, when I differentiate e to the minus x, that minus comes here and becomes a plus e to the minus x over 2, which of course we know is now it's got a plus in there. Now it's the cosh, which of course is what it says. So expect to have to be able to differentiate different trig functions using the definitions of those functions in e to the x. But also be aware that we're meant to know how to do them using kind of the formulaic approach. So if we've got ones like this, tan x, you might recall, for instance, that tan really is sine divided by cosh. And if you remember that, then suddenly you think to yourself, hang on a bit, this is almost like a quotient rule question. So if you like, my u equals sine x, and my du by dx is cosh. My v is the bottom one, which is cosh, and therefore dv by dx. Great thing, of course, about differentiating sine and cosh is you don't get any negative signs. They just stay with the sign whatever they're at now. So using my rule, you might recall it's v du by dx minus u dv by dx all over v squared. So in this case it's v du, and you'll see that's cosh squared, minus sine squared, well, times those two together, all over v squared, which is cosh squared. And that top bit is actually just equal to 1. So it's 1 over cosh squared, which is sesh squared, which hopefully it will say sesh squared here. And you can do a similar thing. Let's just do this last one. Sesh is 1 over cosh. So if I think of that as d dx of 1 over cosh, then I can do this rule again. The 1 is the u now. So I'm just going to use this bit of working out. Well, I'll do it again. I'll write it out. U equals 1 and u dash, it's easy, 0. V equals cosh. And v dash I'm writing out equals sine. So based on that, this it equals obviously v, so it's cosh times that minus that times that, which is sine, over the cosh squared, over the cosh squared, yes, because it's v squared. Now that might be better written as minus sine x over cosh times 1 over cosh. So if you see it like that, then the answer is minus tan x sesh x. Let's see if I've got that. Yeah, minus tan x sesh x. So on that basis, notice some of these I found quite straightforward to differentiate from the e to the x form, and some of them I've chosen to do it properly using just the formulaic approach. Another reminder, we've got the inverse tan of 3x. Well, again, you will recall us doing this in the previous. So if I was to differentiate this, I get dy by dx, and I want to write 1 over 1 plus 3x squared. I have to differentiate the 3 as well and times it, so that sounds like 3 over 1 plus 9x squared. Inverse sine gives me this formula. So this is, when I differentiate it, y by the x equals, it's 1 over the square root of 1 minus, well, my x becomes 5x plus 2 squared. And then I have to times by the differential of this, which is 5, so times 5. That sounds to me like 5 over, what's this give me? This gives me 1 minus 25x squared plus 20x minus, oh, plus 4, sorry. And of course I was thinking that because I'm going to take them all away. So the 1 minus this lot, I reckon, becomes minus 25x squared minus 20x. And I've got 1 minus 4 as well, which is minus 3. It's not very nice, is it? All square rooted at the bottom. So presumably it only works for values of x, which will give us something nicer, which we can square root. And this one, this looks a whole lot nicer. This is dy by the x equals 1, well, what is dy, 1 over that, so it's, in fact it's a minus 1 over the square root of 1 minus 2x squared. And of course now I have to times by this differential of 2x squared, which is 4x. And that's given me minus 4x on the top. And on the bottom, to be honest, after my experience of last time, I would want to leave it alone. But actually it's not so bad this time. It's 4x to the 4. So there's a little reminder of what we've done in the past. Now these are the 3 new formulae then. These are what you are meant to know. I say no because if you look at the formula book for Further Maths, this is what you get given. Now these were the inverse trig ones. You'll notice we're missing one. We're not being given the inverse cos formula. Well, I've written it down in the past of x, but they've slightly improved upon it. They've given a squared here as well, whereas a for me of course was 1. But notice they missed out the inverse cos, and rather bizarrely they've missed out inverse tan. And the other thing I want you to highlight in your mind is they don't actually give me the differentiations at all. They tell me what happens if I integrate it going this way, and so by definition if I differentiate I go back again. And so that's what I mean. If I differentiate sine, let's ignore the a for a moment, think of it as 1. That would be 1 minus x squared, which is of course, oh, well, I haven't got the inverse sine on the thing. Let's do the equivalent here then. Inverse sine, think of that as 1. That's a 1 plus x squared, and that's the formula. Now, it's not very nice. Ignore the log bit for a moment, but the rest of it is not very nice. And also it's not very nice because they don't tell me 2 of the answers. So there you go, you're going to have to learn it. Derive, so let's talk about the proof of this then. Now we've seen a similar proof on these before. The very first thing I'm going to do is move the x over. So I get sine y is equal to the x. And if I differentiate that x, dx by dy, I know will become cos. That's fair enough. And I also know that sine squared, cos squared minus sine squared equals 1. So I've got cos, so I think cos squared is 1 plus the sine squared. And therefore, I'll chuck a y in there or 2, there we go. And therefore cos y is the square root of 1 plus sine squared y. Now of course sine is x, so this becomes cos y equals the square root of 1 plus x squared. So we can sub that back in there, not before first though, because first of all we have to write it as 1 over cos y, because I need dy by dx, not dx by dy, and therefore it's dy by dx is 1 over the square root of 1 plus x squared. So just bear that in mind. Similar I could jump ahead, but I might leave you to do perhaps the than one. If I'll leave you to do this one, see if you can get this answer. Because it's so similar to the last one, you should be able to do it. And the third one, let's see if this one I can do for you. Than y equals x. And therefore, if I differentiate dx with respect to y, I think we saw before that if I differentiate than, I get sesh squared. So that's fair enough. What is sesh squared? Well, there was a formula which I put up just now, which said cos squared y minus sine squared y equals 1. Divide everything by cos, you get 1. Cos squared, sorry. So I'm dividing by cos squared. 1 minus than squared y equals, and that would give me sesh squared y. So I can write this as 1 minus than squared y. And what's than squared? Well, than y is x, so this must be 1 minus x squared. We're nearly there now. So dy by the x is the upside down version of that, which is 1 over 1 minus x squared. So hopefully you've done the one I haven't done, and I've proven the other two for you. These formulas then, you need to learn them, because as I've already shown you, one of them is not given to you. And I've got a final example. It says find the value of the x coordinates of the point on the curve y equals r cosh. Now first of all, r cosh is a posh way of writing inverse cosh. We've seen that before, I hope. And it says find the x which the tangent is parallel to the line y equals x. Okay, so this has a gradient of m equal to 1. So they're saying differentiate it. dy by the x. Well, inverse cosh I know is this, and it says x over 2, so I need to bear that in mind. It's going to become 1 over the square root of x over 2 squared minus 1 times by the differential of x over 2. That's like half x, so times by a half. So that's 1 over 2 square root of x squared over 4 minus 1. Now it says that is equal to 1 because it's parallel to it. So I can now write, and this is the bit, that's where that 1 comes from. So I can now write, if I move that onto the other side, well, I'm going to leave the 2 down now. I'm going to get a half equals the square root of x squared over 4 minus 1. I'll move the square root over to the side. Square of a half is a quarter equals x squared over 4 minus 1. Let's whack it here. Move the 1 over to the other side. I get x squared over 4. It's a quarter plus 1 is 5 over 4. You can see quite easily that x squared therefore equals 5, or x equals root 5. I think that should be the answer. Let's see what I've got. Yeah, x is root 5. So it's a bit of a weird question, but you'll notice all I did was I differentiated it. It told me it's parallel to this line, which of course I know the gradient of, so I set that gradient equal to 1 and then solve the resultant equation. So hopefully that's okay. Well, that's the end of the questions for exercise 7b. Have a look at the textbook questions and get in touch if you get any problems.